Here is my second data. It is also from Kaggle. It is campus recruitment data, which records students' school performance, school major choice, and whether they get a job or not. As you can see here, the size of the second data set is smaller than the previous ones. It only has 15 features and 215 instances. But similar to the previous ones, it also has a mix of numerical and categorical features. The target variable here is the status, which has two classes, placed and not placed. As you can see the distribution here, the placed class is the dominant class here. It has almost 69% in the full data set. It is also the positive class. But because of the major distribution difference, it might affect our prediction result, which I will be showing you later. So here is the second version of my final project. Again, I did an overview of the dataset, and then I removed the ID column and the salary column. I removed the salary column because it's kind of like you get a job and then they offer you salary, so it doesn't relate to whether you get a job or not, so I remove it from the predictors. And then I explored the categorical features to see how many classes are there. As you can see here, it's between 2 to 3 classes, which is perfect. And then I check out the distribution of the numerical features. They are from relatively similar range, 40 to 100, which makes sense because they're all like scores from school. And then I check out if there's any missing values. There's none. And I use box plot to check if there's any outliers. There's some. So I use the z-index to detect where are the outliers. And I go ahead and remove the rows with the outliers. And I go ahead to do some correlation and analysis among the numerical predictors. As you can see here, there does some correlation between target variable and predictors and between predictors themselves. As you can see here, the degree P and SSCP has some strong, not strong, I would say, some but I may do some feature elimination later. And also I use the chi-square test to see if there's any association among categorical variables. And you can see here, there's some strong association here, HSB with the SSCB, so I may remove them later. And there are also some other ones that to reduce the complexity of my model, I may remove them later. And after this test, I go ahead and to look at the distribution of the numerical data. So yeah, they are kind of normal distribution because they are all scores. So if there are a bunch of students, it's more likely for them to have a relatively normal distribution because some people get really good scores, some people not, and most of the ones are between them. So after that, I step into the data cleaning and shaping. First, I split the data because I try to test out the model construction methods that I used for the previous ones. So I also chose KN, decision trees, and SVM for this data set. I constructed one set for the KN, another set for decision trees. I did some z-score standardization. I did some categorical encoding. Because there are some categorical features with binary features, I would just use dummy code if else here. And for ones that have more than 2 classes, I used one hot coding here. And after the nomination and categorical encoding, I put together the SVM train and test set. Okay, so first is the KNN model. Again, I set my original K to 12 because that's the square root of the 115 instances in the train set. And you can see here in confusion matrix, the accuracy is 69%, and the kappa score is 0.28, which is not bad. But looking closer, about 94.9% of the place class is predicted correctly, but only 30.8% of the not place is predicted correctly, which means that the data imbalance is playing some role here, like we don't get enough not placed class being predicted correctly. So I continue to use the ROC curve to see the sensitivity of our model. It's okay. And then I tried alternative K to see if I can improve the KN model. So again, I used a set of K from the range from 6 to 15. As you can see here, the accuracy rate did boost to like 78%, which is decent. It's a good improvement. It's decent. And if we look closer to the 78% accuracy, which is come out when K equals to 10, you can see that the not placed class precision rate jumps to 50%, which is much better than the 30.8% before. That means that the change of the K value did do something. And as we mentioned before, because there's some features are associated or correlated with each other, I decided to remove these two features to see if I can reduce the model complexity to boost the performance. However, after we remove it, we can see the accuracy rate dropped to 76%. Not bad, but also not good. So to be honest, I may keep the two features just in case. And then I built up the decision trees model. As you can see here, I used the C 5.0 package again, and according to the confusion matrix, we got 81.5% of the accuracy rate, which is pretty good. And looking closer, we got 92.3% of the place class classified correctly, while 65.4% of the not placed is predicted correctly. So that's pretty good. But still, we can do a K-fault cross validation to see if the accuracy rate is good for the decision tree model. So as you see here, it's kind of like bounce a little bit between like 60% to like 95%, which is just really good. But the average one is 81%, which is decent. It's okay. So we continue to do some model tuning. As before, I played around with the trials and Wino part to see how they perform. So as you can see here, the best parameter tuning is here, which is when you set the Wino to false and you set the trial to 30, we can get about like 86% of the accuracy rate. And I also go ahead and add some mistake cost to the model, which is as listed here. And then the error, I tried out like multiple error costs, and this is the best result that I get. It's the 83% here, and you can see 92% of the placed class got classified correctly, while 69% of the not placed one got classified correctly, which is a good result. And I continue to build up the SVM model. As you can see here, is 78% accuracy rate with like kappa score at 0.53. 89% of the placed class got correctly, while 61% of the not placed got correctly. So it's good, it's decent, but it's still not as good as the decision tree. And I go ahead to tuning the model with changing the kernel. So the kernel doesn't help changing to the radio basis one. It's down, it's down to like 74.6%. And I also add some cost parameters here. As you can see, the best one is here. This is the elbow point. That's like when the cost value is set to 15. And the overall accuracy rate boosts to 83%, which is decent. So overall, I just want to point out that after the individual model test out, I could see the hyperparameter tuning really change something. It boosts the overall accuracy rate to like 85%, 83%, and most importantly, it also boosts the precision rate of not placed class to like 70%, which is really good because it is not the dominant class. So it's really important to balance our model with the non-dominant class being predicted correctly more often. So anyways, I go ahead and build up the homogeneous ensemble, and I use the random forest again, so it's 81% with a 50.59 kappa score. And I also try out different tree values, and yeah, it's weird, but it doesn't change anything here. It's all stay around 81%. And I also constructed this heterogeneous ensemble function to use the hyperparameters that I used before, that I tested out with the best performance before to build up this one. So yeah, the accuracy rate is 83% and 97% of the placed class being correctly predicted, while 61% of the of the not placed class got predicted correctly. So it's good. But anyways, I think my second version of the final project does show that the techniques that it used to pre-processing the data set and to develop the model does make difference to the accuracy rate, because we started with one that's at 69%, but we end up with something that's at 85%. So I think that's pretty good. That's all for the video presentation. Thank you very much for watching.